Hello, everyone, and welcome to online lecture 11. This is inferential statistics and the beginning of hypothesis testing. We'll have 2 days on hypothesis testing. So I always find this lecture kind of exciting because we are starting to move across this bridge from descriptive statistics to inferential statistics. Now, I will warn you, this bridge can get a little rickety, but hang tight and we will get safely across to the other side. So just to show my excitement that we have moving on to inferential statistics. There you go. Okay, so inferential statistics is the branch of statistics devoted to drawing conclusions, or you might say making inferences about populations based on sample data. So this shouldn't be too new a concept. We did talk about it at the beginning, that our whole goal in statistics, when we have samples, is to be able to make that inference, to draw that conclusion about the population based on our sample. Okay. So what is hypothesis testing then? It's a systematic procedure for deciding whether the results of a research study support a hypothesis. And a hypothesis is a prediction about the outcome of a research study. Okay, so that's all we're talking about, is we want to make this prediction about how the research will go, and then decide whether or not that is going to be something that we have support for or do not have support for. Okay. So now let's go to our next terms, which are our next set of terms, which are independent and dependent variables. The independent variable is a variable that is manipulated or chosen for study. Okay, so this is the one that you are going to either manipulate or just choose to observe. And we'll do some examples so you can see a little bit more about that in just a moment. The dependent variable is the variable that is measured or observed in a study, the outcome variable. So here, I know that sometimes it's difficult to tell the difference between the IV and the DV. Here's a good way to do it. Start with the DV first. Figure out which one is your outcome, which one you're measuring, okay? And then work backwards to the IV. Okay, so let's look at an example together. A sample of persons who happen to try out the new multivitamin vitamin designed to boost energy levels by taking it daily for the past 6 months are selected. Energy levels for vitamin group is compared to the known population energy level at the end of 6 months. Okay, great. So we have a setup. We have some people who happen to try out this new vitamin, and we want to determine what's going on here, okay? So what do you think the IV and DV are? Which one are we measuring? Which one is our outcome? And then from there, maybe go back and think about which one is the IV. Which one did we decide to observe for study or manipulate? And in this case, we didn't manipulate anything. We just chose to observe it. So the IV is the multivitamin use, vitamin or no vitamin. And the DV is our energy levels. Okay, that's what we measured, and that's what is our outcome variable, is energy level. Okay. So, by the way, if you didn't get the reference, vitamin refers to a very old comedy skit in the show I Love Lucy. So yes, she takes vitamin, although her version actually has a great deal of alcohol in it, and it leads to this kind of comedic incident where she is taking way too much vitamin. Okay. Now I'm going to show you a very, very similar example. A random sample of persons are selected to take the new multivitamin, vitamin regimen, daily for 6 months. The energy levels for the vitamin regimen group is compared to the known population energy level at the end of the 6 months. So you may have noticed this is extremely similar to the first example, right? And not surprisingly, same IV, same DV. So what's different? Well, you might have noticed that in the first example, it was a sample of persons who happened to try out the new multivitamin. Whereas in the second example, a random sample of persons are selected to take the new multivitamin. So based on that and that alone, which study is more convincing? Which one do you like better? First one or the second one? So I personally like the second one a whole lot better. And the reason is that I randomly selected people to be in the multivitamin group. And that makes a lot of difference. You see, if I just let people decide to be in the multivitamin group, then there could be a lot of biases. I could be getting a skewed sample. And remember, we really like to have random groups. Okay. So that's which study is more convincing. I would say the second one, the random one, and that's why. So that brings us to this. When you can manipulate your IV, you are on the road to causation. And that's what we did in our second example. We randomly selected who would be in our multivitamin group and who would not. Whereas if we're just choosing it for observation, as we did in our other example, then we can talk about things being related but not causation. Right? So in the first example, we just chose to observe those people who happened to try the multivitamin. And we can talk about them being associated if we found that the multivitamin, excuse me, if we found that the multivitamin led to higher energy levels, let's say, we could say that the multivitamin seems to be related or associated with higher energy levels, but we wouldn't talk about causation. Whereas in that second example, I can't say causation yet because there's a lot more criteria to get to causation, but at least I'm on the road. I'm on that correct path to causation. Now, having said this, I want to point out that there are many studies where we cannot manipulate the IV. And that doesn't mean they're not good studies. They could be very, very interesting, worthwhile studies to conduct, but it's just the case that we can't talk about causation. So let me give you an example. Let's say we wanted to study a younger group of persons versus an older group of persons and look at cognitive memory. Look at memory for a list of words, let's say, okay? So we're looking at some cognitive effect. We're looking at memory for a list of words. That could be a very, very worthwhile and interesting study. But we can't decide. I can't go in and say, okay, you will be 53 years old and in my older group, and you will be 26 years old and in my younger group. I can't tell people what age they are. They come that way, right? Let me give you one more example. Let's talk about the after effects of a natural disaster. So let's say a hurricane, for example. Well, we can't decide who will be involved in a natural disaster or not. That's simply chosen for observation. We might look at people who have been involved in a natural disaster and people who have not and compared their post-traumatic stress levels. It's the effort of showing that maybe that being involved in a natural disaster can have important mental health impacts that we want to try to intervene and assist with. So a worthwhile study, but again, we can't choose who or who's not involved in a natural disaster. Okay, so we like studies that are manipulated by the researcher. We like studies that are chosen for observation. The main idea here is just to know which one you can start to think about. Maybe I'm on the road to causation. All right. So now let's talk about hypotheses a little bit more. So we have two main kinds of hypotheses, the null hypothesis and the alternative hypothesis. Now I'm going to start with the alternative. And this is often abbreviated as H1. There is an effect. There is a significant difference. There is a relationship. In other words, something did happen that's important. Okay. Whereas with the null hypothesis, the H naught or H0, there is no effect, no significant difference, no relationship. So if you had to hazard a guess, which one do you think the researcher is always rooting for? Because we're always rooting for one of these. Yep, it's the alternative. It's the alternative hypothesis. And the researcher has not slept in a while, and that's why they have their big goofy grin on, I guess. But in either case, it is the alternative hypothesis, okay? All right. So now let's do some hypothesis testing for our multivitamin example. The null hypothesis, those taking vitamin regimen do not have significantly higher energy levels compared to the population. And the alternative, those taking vitamin regimen do have significantly higher energy levels compared to the population. So the reason I started with the alternative hypothesis previously, and I recommend doing that in general, is I think it's a little bit easier to state that one. Just say how you're thinking the results are going to come out, how you're hoping the results are going to come out. Those taking vitamin regimen do have significantly higher energy levels compared to the population. That's your researcher hypothesis. That's your alternative hypothesis. Now, once you have that one, and you can generally pull that one right from if it's a word problem, you can generally pull it right out of the word problem. To get the null, add the word not. Those taking vitamin regimen do not have significantly higher energy levels compared to the population. So why is it this one? Why is it do not, as opposed to saying those taking vitamin regimen have significantly lower energy levels compared to the population? Why isn't that our null? So here's why. When you're talking about the alternative and the null, it has to cover the universe of all possible options. So if I said higher energy levels for the alternative and lower energy levels for the null, I haven't covered what if they're the same. So the null is really anything but the alternative. The null is anything but the alternative. So as opposed to saying do, you say do not. So if you just add the word not to your null hypothesis, to your alternative hypothesis, excuse me, you will always come up with a good null hypothesis. So that's our word here to add is the word not, okay? The best way to do it. Okay. So let's talk about what else about a study will make it more convincing. What else about a study will make it more convincing? Well, let's think about that for a moment. Suppose I told you that there were 10 participants in the multivitamin group. Those 10 participants took the multivitamin. And then I told you that there was a significant effect, and those 10 participants had higher energy levels than than those not taking the multivitamin, than the general population. You might say, eh. Now, what if I told you it was 10,000 participants who took the multivitamin and found that they had higher energy levels than the general population? Well, maybe suddenly you're a little bit more convinced. And that's because sample size makes a huge difference in how convincing a study is. Sample size is always a critical component. We'll continue to talk about that as we go forward. But the bigger the sample, the more likely you are to approximate the actual population, and that's why it's more convincing. Okay, so what else about a study makes it more convincing? Okay, so now let's take another example. Let's say I told you that on a 100-point scale with a 10-point standard deviation, that those who took the vitamin D regimen had increased their energy level by half a standard deviation. Again, eh. But what if I now told you that they increased their energy level by 3 standard deviations, or 30 points? Suddenly, you might be a bit more convinced. And that's related to what we call effect size, how big the effect is. Half a standard deviation versus 3 standard deviations. Okay. Okay, so sample size and effect size, both important, both make a study more convincing. Okay, so now I want to remind you of this normal curve, and we can look again and see the percentages that lie under the curve associated with standard deviations away from the mean. So why is this important? Because there's a particular cutoff that we're very interested in the social sciences. And that's the 5% cutoff. So let's look at the top 5% for just a moment. Let's look at the top 5%. If we are looking at the top 5%, we want to say that if the mean for vitamin D regimen use falls in that top 5%, we will reject our null. We will reject that there is not a significantly higher energy level in those taking vitamin D regimen. So we will reject that notion that there is not a higher level in those taking vitamin D regimen. In other words, we will say, look, I think the notion that there is higher levels of energy in those taking vitamin D regimen receives some strong support here. If we fall anywhere else, we will not reject the null. If we fall anywhere else, we will not reject the null. So you might remember that I told you that that z-score of that top 5%, that 1.64, was kind of important. So if our alternative hypothesis is that those taking vitamin D regimen will have significantly higher energy levels, we are hoping that the mean for vitamin D regimen falls above 1.64 standard deviations above the mean. All right. So there's a couple of other important pieces here. Again, here's our main population, and in the darker curve, here's our vitamin D regimen. We also introduced the term alpha here. So what is alpha? Well, we'll talk more about it a little bit later, but for now, I want you to understand that this alpha is where we're setting our cut point. We're setting it at 0.05 or the top 5%. Now we could set our alpha even further out to the top 1% or the top 0.1%. But we generally, for the most part, tend to set it right around 0.05, right around the top 5%. All right. So because we made the prediction that vitamin and vegemin will produce higher energy levels, then we want to see this mean reach all the way up into this gray area, all the way above 1.64 standard deviations above the mean. Okay. Let's look at the other side. Now, let's suppose that we had predicted that vitamin and vegemin is actually kind of dangerous, and we think it's going to actually produce lower energy levels. Lower energy levels. Now we're looking for the opposite effect. Now we're looking for the mean of vitamin and vegemin to fall less than negative 1.64 standard deviations below the mean. If it does, we can reject the null hypothesis. We reject that notion that nothing is going on, because in fact something is going on. Vitamin and vegemin seems to be reducing energy levels. Just like in the previous example, vitamin and vegemin seem to be increasing energy levels. If, however, we fall over here, anywhere but that little gray area, we do not reject the null. We do not reject the null. Okay. So I know that psychology and the behavioral sciences is a very accepting area, but in statistics, we talk about either rejecting the null or not rejecting the null. We never talk about the alternative, and we never talk about acceptance. Just reject or do not reject the null. Okay. So the other thing I want to point out to you guys is that for the past two slides, the title has been one-tailed test or directional. Because we have made a directional statement in our hypothesis about how we think things will go. In the first case, we talked about vitamin and vegemin producing higher energy levels. And in the second case, we talked about vitamin and vegemin producing lower energy levels. Well, what if we don't know? We just think vitamin and vegemin will make a difference, but we can't really commit to which type of difference it will make, higher or lower. We just want to say that those taking vitamin and vegemin will have different energy levels than those not taking vitamin and vegemin. Now, this would be called a two-tailed test or a non-directional. Two-tailed or non-directional test. Okay. Well, this is wonderful, because what I didn't like about the one-tailed test is that I had to commit. You know, I had to say it's going to be higher, and if it didn't come out higher, but it came out way lower, I still didn't get to reject my null. Right? So let's just look at that one more time. In this example, I had to commit and say it would come out way higher. But if it came out way lower, all the way down here, I didn't get to reject. Same here. I had to say it would come out way lower. If it came out to be way higher, I don't get to reject. Now, regardless of whether it comes out way higher or way lower, I get to reject. This is wonderful. This is the two-tailed non-directional hypothesis. So why don't we always do this? I'll tell you why. Because now, as opposed to hitting 1.64, we have to hit 1.96. We have to get beyond, I should say, 1.96 to get into this gray area. And we have to get beyond negative 1.96 to get into this gray area. That's what our z-score has to be. So our alpha stays 0.05. But now that we want to have some in the high end and some in the low end, we have to split this into two pieces. 2.5% here in the upper end and 2.5% here in the lower end gives you 5% total, or 0.05. So now if you fall anywhere in this big middle region, you do not reject the null. But if you fall in the upper end or you fall in the lower end, you get to reject your null. So that's the difference between one-tailed and two-tailed tests. And the way you'll know whether it's a one-tailed or two-tailed test when you're reading a word problem, let's say, is if you see a directional hypothesis, such as higher or lower or greater or smaller or anything like that, versus something saying that it's going to be different, but we're not specifying the direction. It's going to be different, it's going to be associated, it's something like that without specifying the direction. I will tell you that most people prefer and use two-tailed tests because they don't want to take the chance that you make this prediction and then it comes out on the other side. However, if you know enough about a theory or phenomena and you're willing to make that prediction, you get a lot more space. You get a lot more space to fall into this gray area than you do with the two-tail. Okay. All right. So now it is quiz time. Please go to D2L, go to quizzes, go to quiz 4, enter the password 3805, and answer the 2 multiple choice questions. Okay, that's all I have for you guys for today. Stay well, be safe, and I will see you next time.